Maurizio, you can start.
Thank you very much, Luigi. So this is the last lecture of this crash course, and this is taken from chapter 13 of the textbook and lecture number 7 from the David Silver beautiful video course. In this lecture, we are going to talk about completely brand new methods. That means no more value-based methods. So these methods consist in learning directly the policy. Do you remember in the first 3 lectures, we were learning a value function, and then we were using that value function to derive from that the policy for instance, with greedy improvement or with epsilon greedy improvement and so on. Starting from now, we are just learning the policy. This kind of reinforcement learning is, of course, called, instead of value-based reinforcement learning, is called policy-based reinforcement learning. We say also that we are doing policy learning. The reason to do this is clear. I mean, it's a famous sentence from Vapnik in February 98. He stated, obviously, never try to solve a more general problem as an intermediate step. And in this case, we were looking for the policy from the beginning. Remember, I told you the problem in a Markov decision process is to find the optimal policy. So the thing we are looking for has always been the policy. And we were trying to learn a proxy, a value function, using which we were going to target the policy. From now on, we just learn the policy. So no more general policy iteration. Remember, this means find the value, then improve the corresponding policy, find the new value, improve the corresponding policy, and so on. This is no more general policy iteration. Okay, and this is what we are doing. Since we are also starting from lecture 3 in doing function approximation, the policy will be approximated, will be parameterized. And we call the parameter theta to distinguish it from W that we were using in the last lecture for parameters for the value function. Sometimes, almost often, you need also a value function to approximate. So you have both theta and the W for the value function approximator. And we will write this way or this way, the dependence from theta. And the rest is, as usual, the policy. That means the probability of choosing an action given that you are in some state. And of course, now this probability is conditioned also on the parameter. So we have same kind of problems and as in the last lecture. That means we are going to have a space of representable policies and so on. Just a remark, the parameterizing the policy, this includes also, maybe it was not clear, but includes also the tabular case. I mean, what I'm going to say here, you can do also in the tabular case. That means that simply every parameter corresponds to a value. So you are learning actually parameters, but parameters are actually the single action state value functions. Just a small detail. Okay, so how do we parameterize the policy? A common way to do this is parameterize something which is called the preferences for the policy. that here in the slide are denoted by H. This is the preferences. This is a preference for the choice of action A in state S corresponding to the parameter theta. And in order to produce from the preferences a probability distribution, then you just apply a softmax function. Just in case you are not familiar with this, nothing to be scared of. This is clearly single value. On the denominator, you have the sum of all the values. So you are just normalizing each value, and clearly all of them now sum to 1. So this is a probability distribution. This kind of technique, let's call noble way, is called applying a softmax activation, or applying a softmax function, and so on. Softmax activation is a term that you heard a lot when using neural networks. Typically, the last layer of your neural network approximating the policy, because the policy approximator will be usually a deep neural network, the last layer is a softmax layer. So whatever comes before the last layer is just learning preferences for state inductions. Usually, sometimes you want to control how much this kind of distribution can or can't be deterministic. You do this with something which is called the temperature. Imagine putting here in every term taking a fraction by a parameter that you call temperature for physical meaning, because this is called the Boltzmann distribution in physics. Can you see what is happening? The more the temperature is increasing, and the less you are noticing differences between preferences, because this is going to 0. And so everything is becoming closer and closer. And if the temperature is increasing, then the policy is flattening. And on the opposite, if the temperature is going to 0, the policy is going to give you just the action with the maximum preference. And this is also why this is called softmax. In some sense, it's a smooth version of the maximum function, converging to the maximum function when theta is converging to 0. Okay, how to compute this kind of preferences? Well, you can do as usual, as you like. Preferences can be computed by linear approximation, as we said in the last lecture, and in this case using features, or by a neural network with weights, maybe a deep neural network. And this later one is the approach used by Alphago and all of its derivatives. And using softmax is almost recommended. I mean, it's very good from several points of view. For instance, softmax is a flexible choice, because remember, sometimes in some problems, the optimal policy is deterministic. And if this happens, the parameters can learn preferences that will drive the optimal actions to the deterministic one, meaning, for what I told you before, the preference for the optimal action will be driven to be very big, and so overcoming every other preference for the action. And on the other way, flexibility means that can do also the opposite, can approximate a stochastic policy. That, if you remember, that was a problem with greedy improvement. If you do greedy improvement, you obtain a policy which is essentially deterministic. And in this case, you can approximate a stochastic policy. Okay? Do you have questions on this? There should be a question, actually. Okay, since I want to go a little bit more quicker than the previous lectures, I will ask the questions that you were supposed to ask. That is, can the preferences be the action values for the Q values of the pair state actions? I mean, this is a question you should ask because usually at this time in the lecture, this question is asked. So if you're wondering if these preferences can be the Q values, well, the answer is yes and no. I mean, if you use the Q values as preferences, you are saying that you're learning the Q values with a different method. So you're not doing policy learning. You are learning the value, and then you're using the Q values to parameterize, in some sense, to give a stochastic policy. Okay, and this can be done. I repeat, in this sense, the answer is yes. This can be done, and it is actually one of the several solutions to the exploration-exploitation dilemma that we told in the last lectures, and that was solved just by using epsilon greedy improvement. If you remember, the epsilon greedy was taken instead of greedy choice because epsilon greedy was able to explore always, never giving up exploration. Okay, this would be a different way to solve the exploration exploitation dilemma, that is learning Q values and using them with a softmax policy. If you do this, you say that you're using a scheduling known as Boltzmann exploration in your algorithm, but that wouldn't be policy learning. So the answer, can we do policy learning using as preferences the Q values, in this sense is no. Okay, that's enough. As usually, please interrupt me if you have questions. So now this is a typical picture that I'm showing you. We have methods based on value function. We have methods based on policy function. That means learning the policy, learning the value. These methods are called policy-based. These methods are called value-based, as you already know. And you have some intersection. This intersection is when you learn the policy and you also learn a value function. In this case, this is not really precise, but in this case, quite often, the method that you are using is called an actor-critic method. Remember, when you hear this term, that the actor is the policy is acting, is choosing actively the actions, and the value function is the critic in this respect, because usually the value function is used to tell to the policy whether the action chosen by the policy, the actor, were good or bad. So in some sense, it is criticizing the actor. Okay, just a matter of terminology. Advantages of learning a policy. Well, the policy, learning a policy can be used also when you have continuous action spaces, because in that case you can just learn the parameters of a continuous distribution. For instance, stating that your policy should be Gaussian, you can just learn the two parameters of the Gaussian distribution. As I said, so this is the first one, as I said, we can learn both stochastic and deterministic policy. And this is also another thing very nice. Maybe it's not evident, but if you think about it, a policy can be simpler than the value function. Just imagine a maze, let's call it a maze, with a very, very complicated value function but where the correct way to reach the exit is just going straight forward. You always have to choose the same action for 100 consecutive steps. In this case, the policy is very simple, but assuming that the value function, and you can build such examples actually, assuming that the value function is complicated, the value-based method would take much more time to find the optimal policy. And of course, if you know in advance that the policy has a certain shape, you have some reason, qualitative reason usually, empirical reason to think that your policy should be more concentrated in certain actions and less concentrated in other actions. You can start with a parameterization which is already giving more importance to the more important actions and vice versa for the less important actions. This means that you can inject prior knowledge about the desired form of the policy, assuming that you have such prior knowledge. And quite often, this is the most important reason for choosing between policy learning and value-based learning. Moreover, have you ever thought about this the last week? I don't know, I should have said, maybe I said, actually, I don't remember, that when you're doing epsilon greedy improvement, as soon as one single action acquires a Q value bigger than the previous one of a different action, I mean, as soon as an action becomes the new best action, the epsilon greedy policy drastically change, right? Because before that policy was choosing the optimal action with probability 90%. And now the new policy, at the next step, without continuity, the new policy is abruptly choosing a new action with 90%. Okay, this is usually bad because if you have such a non-smooth change of action probabilities, then the convergence of the method will probably be slower and worse, probably. Okay, of course, there are some disadvantages of policy learning. Typically, you will converge to a local rather than a global optimum. And evaluating a policy, we will see an example, is typically inefficient and with high variance. Okay, let's have a look at an example.
I have a question before
yes,
the slide.
Yes.
So it is typically converged to local also if we use a neural network.
Yes.
Okay.
So the question was
if I use a neural network to compute the H.
Yes, you let's say you always use a neural network to compute the preferences.
Okay. Okay.
So the question is if
yes,
whether you use a neural
you can
network.
choose between a linear approximation or a neural network.
Okay, so, let's say I shouldn't say this, but forget linear approximation. I mean, if the problem can be solved with a linear approximation, then please do it, of course. Okay, but usually complex problems can't be solved with linear approximation. So that, and this is what reinforcement learning is for solving real, very, very, very complex problems. So of course, if you can solve it with a tabular, if you can solve it solving a linear system, do it. If you can solve it with dynamic programming, tabular solutions, do it. If you can solve it with approximate dynamic programming, that was lecture 1, do it. But usually you can't use dynamic programming. You need to use model-free methods, and probably you can't use tabular methods. You to use approximation. In that case, the simplest thing you can do is using linear approximation. Please do it, but be aware that usually linear approximation doesn't work very well on very complex problems. Of course, in this setting, there is also the notion of explainability. And so if you use a linear approximation, then you have features that can be easily explained, evaluated, and so on. If you use a black box like a deep neural network, you are probably solving much better the problem, but you don't know how. In some settings, some context, this can be a problem. For instance, for pharmacological indications. I mean, please tell the patient to take a drug without telling him why. Oh yes, the machine told me that with this drug you will be cured. Okay. Okay, sorry for the digression.
Okay.
Answering your
anyway,
question.
there is no theoretical proof that I can reach this global optimum. I mean, this is just an empirical evidence, right?
Oh, you mean with linear approximation?
With a neural network.
With a neural network, you never reach the global. You reach a local optimum.
Yeah, this is an empirical evidence. I mean, that I can reach the global optimum, because I do not have a theoretical proof of this.
The methods we are going to talk about are gradient methods. So unless you are very, very lucky that you start from an initial condition which is quite close to the global optimum, then the gradient method will converge to the closest local optimum, right?
Okay.
So this is, I mean, this is a theoretical argument, and more than empirical evidence, I would call it a probabilistic reason. The reason is the following: when you use a neural network with 1 million parameters, and this is a small number of parameters, you have the loss function, which is a function over 1 million parameters. So the graph is in R to the power of 1 million plus 1, right? And so the landscape is called of the loss function is very, very complex, and the probability in terms of stochastic argument, the probabilistic argument that you are choosing an initial condition to start with your gradient descent method or some other methods that try to optimize the function, that you start close to the global optimum is very, very close to zero. Okay. It depends, of course, on the surface, but we are assuming a complex problem with a very complex loss function shape, loss function graph. So I would say more than empirical, the reason is probabilistic and in this sense theoretical. Actually, I would say from the empirical point of view, there is almost the opposite evidence. That is, the problem is solved very well using a neural network often. That means that you are probably quite close to the global optimum. The accepted reason for this today is that the landscape of the loss function is so complex that there are several, but really several local minimum, which are actually more or less at the same height as the global minimum. And so you are finding local minimum, but they work approximatively as well as the global minimum that you are not going to find explicitly. Okay?
Yes, thank you.
Okay, sorry for the long digression. That's more related to neural networks, not to the reinforcement learning problem. Now, let's have a look at this, this picture. This is called short corridor problem. What is this? You have 3 states, actually 4 states, including the last one. Okay, let's say You have state 1, which is the starting state, 2, 3, and the terminal 1. And this is a grid work problem. As usual, you can go left and right, and every step you take, you have a reward of -1. You have 4 states, as I said. You have 2 actions, left and right per state. Now, this short corridor problem has a small problem in the state number 2, meaning that the left action in the state number 2 and only in the state number 2 will take you to the right. You see, this is expressed by this picture. If you go left, you will go actually to the right, to state number 3. If you go right, you will end in the starting state. Okay, only in the state number 2. Now, if you have a tabular method, no problem at all. This is a toy problem solved in half a second. But assume now you are approximating states. Okay, you are doing an approximation using an approximation method that is not able to distinguish between states. All the non-terminal states look the same. So in your approximation, state 1, state 2, and state 3 are exactly the same. You understand the problem, okay? You have 3 states, but you have just 1 parameter to learn. So you can just learn the value for 1 parameter that will represent the 3 states. Okay, this is what you are doing when you're doing approximation. You're using less parameters than states. What happens now? This means that a policy, in this approximation, a policy will assign probabilities to the single state, probabilities for the 2 actions. Quindi you will have a policy giving that S left as probability something, and the probability of S right is the 1 minus the first number. Okay, so these are all the policy. Now assume you are considering the policy parameterizing with respect to the probability of right action. Okay, so let's call this P, and so this is 1 minus P. And so assuming this graph, there is this probability P. In this graph, you can find the value of the policy according to the given probability to the right action. From this graph, you can compute actually these numbers, and you see that the optimal policy is the one corresponding with P more or less 0 dot something like this, 54. Okay, but assume you're using a value-based method using epsilon greedy the policy. Epsilon greedy action value methods would choose the policy go right with probability 1 minus epsilon and go left with probability 1 minus epsilon. Okay, so an epsilon greedy method would choose just between 2 different policies which have a fixed epsilon. Okay, 1 minus epsilon or 1 minus epsilon over 2. It depends on how you define the epsilon greedy policy. And in the picture, you can see that the policy going left almost all the times, that means the policy epsilon greedy left in this way, with epsilon equal to 0.1, 0.1 is assuming a very, very small value, less than minus 82. If you take the policy going almost always right, then it's a little bit better, but far from the optimal one still. The optimal policy get this number. So you can see if you're using an epsilon greedy method, value-based epsilon greedy method, the epsilon greedy policy can't reach the performance of the optimal stochastic policy that you can instead find with policy learning methods. Okay, is this clear? I mean, this is a very simple example, but I think it's giving some light on why one should use policy learning, what one should learn a policy. In some sense, the problem in the epsilon greedy policy, the problem is that the epsilon, the exploration parameter, is not learned. You're not learning epsilon. You are choosing epsilon from the beginning, and then you have just two different policies to choose from. This is, of course, due to the fact that you are approximating. You are aggregating three states into one. You cannot distinguish between them. Okay. That should be enough. Interrupt me if you like. Otherwise, we are going to next section. Objective function. As we did in the approximation part, when we say, okay, we will learn this with this approximation, this parametric approximation, we need to say what is the objective to optimize. Okay, we need to move the parameters in the direction of some optimization objective. In this case, well, the question is easily answered. I mean, it's very natural. If you want to evaluate a policy, what can you do? Well, you can take the starting state in an episodic environment. For instance, if you have one single starting state, you can take this starting state and evaluate the value of that state under the policy. Okay, this is very natural. I mean, if your episodes all starts from the same starting state and you compute the value of the starting state, this is a very natural number synthesizing, telling you how good is your policy. Okay, and if you're, of course, if your episodic environment is not starting from a single state, you take the expectation of the value of S theta, where S is taken from the initial distribution. Okay, from the, how can we call it, raw initial distribution. But in these slides, in the computation we're going to do, this is not really relevant for the proof. So we will just think about a single starting state. Okay, so from now on, think about an episodic environment, an episodic Markov decision process, where every episode starts from the same state as 0. Okay, so this is the value of the policy. And of course, we want to maximize this value, not minimize. So we are using gradient ascent. Of course, this implies that we are choosing smooth approximators. Okay, there are several families of approximation methods. We are using a method where we can use the gradient descent, the gradient ascent. Okay. Okay, the question is telling you, okay, but if we are not in an episodic task, what we can do? If we are not in an episodic task, we don't have a starting state. The process is just going on forever. But in this case, under certain conditions, we have the limiting distribution, the steady state distribution, the stationary distribution of the underlying Markov process, and we can use that distribution to weight the value of the states. Also very natural, right? And just let you notice that this distribution is just what we call the on policy distribution in the policy distribution in function approximation lecture. Okay, and just let you notice, as written in the box, that in continuing environments, we have two different notions of value of the policy. This is one, the easiest one, and this is another one with several advantages and so on, just to let you know. But I repeat, in this lecture, just think about the episodic setting with a single starting state. Okay. Well, we're going very fast. So, how to compute the gradient? Well, the first line in the box, I put it because I always like to remember that sometimes there are very simple methods that works. One way of computing the derivative of this objective function, let's call it, no, I don't want to call it a loss because we need to maximize it, is the average value of states. One way is to do just the incremental ratio. I mean, this is the very definition of the derivative. Well, sometimes this method works. So sometimes it is simple and effective. Well, this is not the topic of this lecture, of course. But please notice that this method works also if the parameterization is not differentiable. Okay, but in our case, this method we assume doesn't work. Our policy is differentiable. And now here I have a question that I invite you to look and to try to answer. The question is the following. The objective function, that is the value of the starting state, remember, under the policy parameterized by this parameter, depends on two things, here labeled as A and B. Well, first, action selections. That means that while we are making the episode, we are choosing actions according to the policy. And then it depends also on the underlying model, that is the distribution of states where those selections are made. Which one between these 2 points you think is the bigger problem for the computation of the gradient? We want to compute the gradient, right? So this is the question. Choose one between A and B and tell me why you think that is a big problem and the other is not. So remember, yeah, this policy, I follow the policy, I do this. Until I reach the last reward, the last state, which I don't care, the terminal state. And the objective function is just the sum of the reward. 1 plus R2 plus up plus RT, with the discount factor, of course. okay, the expectation of this. And in all of this, the states appears according to the model, and actions are given by the policy. Please give me a sign that you are hearing me.
Can I prove?
Say it again.
Can I prove to say?
Yes, yes, of course.
So if it works, if the policy is not differentiable, I don't think this is a problem. So maybe it's A.
What do you mean by the? I mean, here the policy is differentiable. Yes, and so you say A can be a problem. Well, of course, I'm not saying that the computation of the gradient is easy, but the dependence on the actions from the policy, these actions are just chosen according to pi theta. And so here you have a dependence from the parametrization that is by definition exactly what you know. So when it comes that you need to take derivatives of this parameterization, oh, I see your point. Yes, of course, if the policy is not differentiable, when you are trying to take derivatives of this part, you have a problem. You are right. But I say the policy is differentiable. Otherwise, we are not trying to take the gradient. So in this case, this is not a problem. You just take the derivatives of this. Just if you take a neural network, you will just use the famous backpropagation method to get the derivatives of the with respect to the parameters. But on the other side, the states that you encounter, and remember that in order to take the expectation, you need to take count of how many times you meet a certain state, because you have to count that state for that many times in the expectation. The distribution of counts of how many times you encounter every single state depends on the model. And please don't forget that we are still in the model free case. This is from lecture 2, was not only for lecture 2, but starting at lecture 2, we said no more model. From now on, we don't have the model. Okay, this means that when we will write this kind of objective, which is the value of S0, we will write it recursively, and we will try to compute the gradient, then the model will be a problem. Okay, so how can we compute the gradient? Let's start with some simple computation. So for now, I will consider a very, very simple one-step MDP. Very simple, means just one state. Okay, every episode starts from a state S0. You do one action and terminates after one time step with a certain reward. And the exercise that I'm now going to do is the computation of the gradient of this function. So you can start looking at how this works. Okay. I wrote this here. I will comment this computation. So please tell me if you are not understanding what we are doing, because now we are doing this several times in a much more complicated fashion. I'm taking the derivatives. First, the derivatives that I'm talking about are with respect to the parameters, okay? Because I want to optimize J with respect to the parameters. I want to find between all the policies that I can represent with my parameters, I want to find the one which is best. So I have a notion of to be best as the optimum of this function j, and then I follow the gradient ascent. I go toward the direction that the gradient is showing me, because I know that the gradient points to the quickest increasing direction for a graph. Okay, so first I just write the definition of J. Can you recognize that this is the definition? This is the first point. I am state S0. I want to compute the value of S0, right? The value what is the value that I can obtain doing one action, and from now on taking the value of everything that I get. This is also known as the value of the action. Okay, so this is known as the Q value of the action A taken from state S0. But then to count the value of S0, I need all the other values of the other actions. So if I have another action, I will take its Q value of this other action. Let's say this action is A, this is A tilde. And then in order to obtain the value of this state, the value of S0, this is just the average of the remaining values, average expected value with respect to the probability of the actions. Okay, and so I'm just taking the sum over every action of the probability of the action from the state S0 times the Q value of this action, which is exactly this part. Okay. Well, the derivative, I can apply the product rule. And so I have the derivative of the policy here. Very good. I say that the derivative of the policy can be done. And here I have this part. Now, think in our approximation, in our very simple MDP, when I take one action, I finish. I arrive at the end of the episode. It is a one-step MDP. So now there are no more actions to take. So there is no more dependence from the policy, right? Because the state is terminal, no actions from there. So this part just disappears, and we obtain just this. Why this is better than this? Exactly for the reason I was telling you. This is computable. I mean, I parameterize my policy and I have the gradient, you see? As soon as I can compute the gradient of the policy, and if I can't, then there is no reason to go forward in this argument. I can't compute the gradient, of course. If I can compute the gradient of the object that I need to optimize. And is this clear in this very simple case?
Yes.
Okay. So now we want to understand the proof in the general case. What happens when I'm here? Okay, I'm not in a terminal state, so there is still dependency from the actions. Okay, I can show you this one should be, yes. Okay, the theorem we are trying to prove is called policy gradient theorem. Okay, and I will give you the final statement in the next slide. But for the moment, let's try to follow the book. The reason why I'm showing you this in the book is because I think it is very well written. So up to a certain point, it can be followed. No reason to rewrite things that are already written very good. You see, everything is commented here. The book gives you the reason why it is doing this, and it is also sort of offending sometimes. So this is telling you that derivatives satisfy the product rule. Okay, so this is what I did before. So you have this derivative. Now here you're just applying the definition of Q value. Okay, just look, I cannot annotate here, but the Q value is just you are in a state S. You take one action A, and from here you look at the state S prime, you get a reward, of course, and you weight with this probability what you obtain. How much do you obtain? The reward plus the value of the next state. Remember that this value of the next state is including all the next returns. This is the Bellman equation in some sense. The Bellman equation for the Q value where the state value function is not expanded into Q values itself. Okay, it's the relation, the definition of Q value. What I obtain when I do action A from the state S. Well, what I obtain is this. Okay, of course, I can land in every other state. So I'm not doing this just for one single state as prime. I need to sum over every other state and every other possible reward. Okay, so here I'm writing this in this way. Look, I'm taking inside the derivative, of course, the derivative of the sum, and I'm considering the fact that the reward doesn't depend on the policy. Remember, I'm taking the derivatives with respect to the parameters. So derivatives only on the value function here, weighted by the model, of course. And now look, this is the derivative of the value function of a state. But what we were calculating was exactly the derivative of the value function of a state. So I can plug this equivalence inside this value. And this is called, you see, unrolling. This is very common in reinforcement learning. This is why I'm showing it to you with such a detail. Because due to the recursive nature of Markov decision process, that is, remember, there is the Bellman equation. The reward is recursively defined as the immediate, the return is recursively defined as the immediate reward plus the next return. This gives every problem related to MDP a recursive structure, and it is quite common doing something like this, some unrolling properties, plugging in an equation, the value that you are looking for in this moment. So if you plug all this part here, making the right replacement with symbols and so on, you obtain something long like this. This is just this plugged in. And from this, you obtain this last equality. This last equality is a bit obscure here on the book. You need a certain calculation to understand it, okay? I have found a good explanation on a website that I'm showing now to you, and then we will try to do this by hand. This is the calculation that you you can use this website when you are studying the lectures and so on. You can see this part is just what I was telling you, the Sutton and Bartow part. And now that single equation is explained in this long way. You can see it's not really very, very trivial. And this is what I'm now trying to explain to you. The link to this web page is in the slides, of course. Okay, so let's go back to the original slide. Okay, look at this one. Okay, insert a page, and we try to give you the idea of what we are doing. So first I rewrite the last part. So we arrived at nabla theta of the value function of S equal to, we have the sum over all the action, and then we have nabla. Let me omit nabla theta, okay? And also the pi is depending on theta. Okay, here we can put the action from the state S. Here we have the Q value. This is Q pi, of course, but I will omit it. Pi is fixed for the moment, so no reason to be more precise. And here I have again pi theta A over S, which is weighting. This is the sum over all actions here, and this is weighting, the sum over all next states of the model given S and A, the probability of landing state S prime, and this was weighting the derivative of the value function of S prime. Okay, this is what I showed you on the book. Okay. Now, to simplify things, we can write this way. This part, which is appearing, this part, which is the part we are interested in, we call it phi of S. So phi of S is the sum over A of the gradient of pi, A over S of QSA. Okay, so this equation now is that the gradient of the B function of S is just phi of S, this part, plus the sum is distributed, yes, pi AS, and still we have S prime, pi of S prime SA, and here I have nabla theta nabla VS prime. Okay, let's divide it. Okay, for the moment, I'm just making formal computation. You remember what, please take in mind what I'm doing. I'm doing the computation of the gradient of the objective function, and I am unrolling it because here now I'm going to put this same expression. Okay, I haven't unrolled it yet. I'm just writing it in a lighter way, isolating this term. Okay, so let's go on. Phi of S. The summation can be put all together, so plus sum over S prime, sum over A, pi A S, model A S, and V S prime. Okay, so now this is the crucial point to understand. This part is just the probability of going from S to S prime in exactly one step. Have a look at it and tell me if you're not convinced. I start in state S, I take action A, and now, assuming that I started in S and taken action A, what is the probability of landing in S prime? This one. So this is the product of these two probabilities, is the probability of starting from the state S and landing in S prime by taking action A. Okay? Is this clear? Once I sum over every action, what I obtain is just the probability of going from S to S prime in exactly one step. Okay, because otherwise I have to multiply for other probabilities. Okay, if you understand this, and if you accept that this probability, by definition, we write this way, rho pi of going from S to S prime in one step. This is the notation used in the website, so I'm using the same. And now you can write this as phi S plus sum over S prime, the probability of going from S to S prime in one step, times nabla V S prime. Okay, and now finally we can plug and make the unrolling, that is phi S plus sum over S prime, probability of going from S to S prime in one step. And now this is nabla V S prime, this is nabla V S, that is this. So now times, and here I will put the exact same thing, but with S prime instead of S. So phi of S prime plus sum over, well, not S prime, so let's say S2 primes. The probability of going from the state S, which is actually S prime, to the state S prime, which is actually S2, in exactly one step, times nabla V of S2. Okay? So I feel a little bit alone. Can somebody help me? Because it's sort of, I mean, I'm talking to.
I think it makes sense to find.
Yeah, it's clear.
Yeah.
Yeah.
Okay. Can somebody just follow me or take your mic on and you just say yes when I say, is it okay?
Great. Sure.
Okay, thank you. So, sorry guys, but this online teaching is stressing from this point of view. Okay, so I'm just now doing this in multiplication. So S prime, this is the probability of going from S to S1 in one step. times phi of S prime plus the sum over S2 of the probability of going from this. Okay, I have to multiply. Okay, yes, this is the other point, exactly, and then we are. Now I have to multiply this probability of going from S to S prime in one step with the probability of going from S prime to S2 in one step. What is this? The probability of going from S to S prime in one step times going from S prime to S2 in one step.
Is the probability to go from S to S2 prime in 2 steps?
Perfect. Very good. Thank you very much. Times phi S. What is this? 5 seconds. Oh no. Oh, times the nabla v of S second. Okay, now if you think a little bit of iterating this this argument, then now you unroll again with this one, and you put all together here, and at the end, what you obtain is phi of S plus the sum on S prime of the probability of going from S to S prime in one step plus times times phi S prime plus the probability of going from S to S double prime in 2 steps times phi of S double prime plus the same probability of going from S to S3 primes in 3 steps and so on. So at the end, you can write all of this as all of this is multiplied by phi of S, that is phi of S prime, phi of S2 primes, and so on. So let's call this phi of X, and let's say X is in the state space. And here you have the probability of going from S to X in K steps, and you have the sum over K going from 0 to infinity. Okay, at least it makes sense. I mean, maybe some details you should look by yourself, but I'm just unrolling this for up to infinity. This was unrolled for 2 times.
Yes.
Okay.
Absolutely.
Okay, perfect. So, what are we going now to do with this? Remember that this is, I write this here, this is the, at the end, if you put here, you have this, which is the derivative of the value function of the state S. Okay, this is the state S. And this was the derivative of J of theta. It was what we wanted. But actually, this is not true. The derivative of J of theta is the derivative of J of theta is nabla V of S0, remember. So now we rewrite this for this quantity, which is nabla V of S0, which is, for all this written here, the sum over K goes from 0 to infinity of the probability of going from S0 to, and now makes no sense anymore calling this X because we don't have S used, so I will use the usual symbol for the state. So going from S to S0 to S in k steps phi of S. Okay. And I call this just sum over S. All of this, I will call it mi of S times phi of S. This phi and this phi are the same, of course. Okay, so we are almost there. I just let you notice that this is the probability of going from S0 to a certain state S in a certain number of steps. So this is the probability in some sense. This is a measure of how often we are meeting the state S, starting from S0. Do you, does this ring a bell of something we already told before? How many times, a measure of how many times we are encountering a state. You should remember the
formula before where this was what was missing essentially. The
yes,
information.
but I used in the also in the last lecture we used quite often a certain term for the importance of the states.
Was the in policy distribution.
On policy, perfect, very good. It is called the on policy distribution. Remember, the on policy distribution is the policy that you use when you do on policy learning, that is in some sense measuring how much visits you are, how much times you are going to visit a certain state. It is a natural measure of importance, okay? And I told you in some just drafted way that this is the limiting distribution or the normalized count of visits and so on. And now this is sort of the same thing in a more formal way. This is what we were talking about, okay? For the moment, this is not yet distribution, at least in the episodic case, because you remember in the episodic case, there is a terminal state. So this sequence, this infinite sum is actually finite. But what you do this here is the following. You just isolate this big sum over S, and so that you can normalize internally this mi of S over the sum. And here I can still put S. Okay, maybe I should use S prime times phi of S. And so this is a constant. Okay, you sum over every state S. So now we can say that all this quantity is just proportional to the internal part, that is the sum of mi of S over the sum of mi of S times phi of S, and all this number, this is what is usually called the on policy distribution. Okay, so now you have also the formal definition of the on policy distribution. This is the usual notation in our slides. This is actually, I think, mu of S. And this is the way to measure the importance of the state. You see, in the episodic case, this is just the normalized count of how many times the state is visited during an episode. Okay. And remember, this one was the sum over A of the gradient of the, let's write first the Q value. The Q value of SA times the gradient of the policy. Okay. So, well, you didn't realize, but we have proved the theorem. And the theorem is, remember this part. So the theorem is that the gradient of the objective with respect to theta is given by not equal, but up to a constant, is given by the sum over S of the importance of the states under that policy times the Q value times the gradient of the policy. Guys, this is one of the most important theorems in reinforcement learning, and it is called the policy gradient theorem. And I'm going to show it to you on the slides, actually. So remember this, okay? Proportional, this symbol means proportional. And here you have a weighted sum. This is a probability distribution. Remember, it's a normalized count. These are frequencies. You can use them as probabilities. So you're just weighting this quantity by the natural distribution of the environment. Remember this. And this is what we obtained. So this is the analytical computation of the gradient of your objective, which is a constant times these weights, okay? The normalized count for the episodic and the steady state distribution for the continuing case. And this is the other part of the story. And here you can find what is K and what is me. Okay, the proof is the one I've given to you. You can find the initial part of the proof in Sutton and Barto, and the last part is clearly explained at this link, or otherwise you can just look all on this link. There is the whole proof. Okay, do you have questions on this? So this is called policy gradient theorem. This is from 98. Actually, the policy gradient theorem is from 97, but in this form, it was given by Sutton, I guess, in 98. And now the problem is how to compute it. Okay, this is the theory. This is the gradient. And now we want to use this expression to compute the gradient. For the moment, it's not apparent that this is simpler than the original definition. In particular, if you want to compute, okay, question for you. Show me that you're still online, telling me, by giving me an answer to this question, if you want to compute these quantities, which one is the difficult one? I mean, K is a constant, it's not a problem, forget it. Between this summation and this, what is the one that is giving to you more problems? The answer is similar to the one before.
Maybe the on-policy distribution.
The on-policy distribution, because the on-policy distribution is containing the model again. Okay, is related to the transitions, right? So it's difficult to count, to estimate, and so on. So we are now trying to do something to compute this, and the strategy is always the same. Remember, we are following, starting from the approximation lecture, we are following a similar overall strategy that I repeat again. We are computing, we are rewriting quantities we are interested in by expectations. And then we are estimating these expected values by sampling. Okay, so according to this overall strategy, if we now can write the gradient as an expected value, then we can sample it. And the problem of computing this this gradient is solved. Okay, so the question now is, can you write this sum, double sum, as an expectation? And I more or less already have given you the answer before by speaking. I prepare the pen and I wait for somebody to tell me the answer. This is the expected value under some probability distribution of something. So you have to tell me this something and the probability distribution that I used to sample.
Well, the on-policy distribution is the probability one.
Exactly. The on-policy distribution is a distribution. So this is apparently an expected value, right? So as soon as I write here that S is taken from the on-policy distribution, and if I want to be precise that A is taken from pi, then I can say that this is just the expectation of these quantities. Nabla pi theta AS. Okay. And now this means that if I can sample states according to the on-policy distribution, and if I can sample actions according to the policy, which of course I can, then I can sample values from this expectation. So the question is, can I sample states from the on-policy distribution? Answer, yes. Just follow trajectories. Remember, the same in the last lecture, this on-policy distribution is not clear that it is the good answer in the value, in the function approximation value-based methods, the good answer for solving the reinforcement learning problem, but it is a very nice strategy to follow. Okay, because we just follow episodes. We just let the environment be itself. Okay. So we have, I guess, here the answer. Okay, very good. And now, yes, the answer is this. And now look, remember, this is the gradient of the objective. As soon as we can sample this gradient, we can update the parameters in some way like this. We can say that the parameter at time t plus 1 is the same as the parameter at times t plus alpha times this gradient, theta t, theta at times t. Okay, this is what we are looking for. Okay, this is why we are looking for an estimate of this. So usually we want something which is an estimate of this. We write this in this way with the hat. And now we can have such an estimate. Can you tell me such an estimate? This gradient is an expectation.
The mean squared error.
No, you have a.
We can use the sample mean.
Yes.
Yeah, so Monte Carlo estimated.
Yes, Monte Carlo estimates, but I mean, Monte Carlo estimates arise when you put here 1 over the 1 over t plus 1, okay? And then you have the empirical mean, you have Monte Carlo estimates and so on. You just take one sample.
Yes,
remember,
that was
this
yeah,
is
meant
strange because you are estimating an expected value just by one sample. The same if I ask you to estimate the expected value of the of throwing a dice by just throwing it once. But this is what we are doing. Just throw it once. Just take one sample. And so what does this mean? You just take this. You just take this expression. That means you take the sum over all the actions of the Q value of SA. Now we are going to have another problem, of course, times the gradient of the policy action A, and the state. Remember, the state must be sampled from the on policy distribution, right? And so here you will write simply ST. That means that you are following the trajectory.
Sorry, one question. This is because we are just looking at one step ahead, right?
At one step, yes.
Okay.
We are just looking one step.
Okay.
Just one step. But here we still have a problem. We don't have the Q value function of the, I mean, if you had the Q value of the action for states, and here is ST, of course, then you solve the problem. We need an estimate of this. Okay, it's not a problem. We just take any estimate of this Q value. Okay, so not with pi, probably with the value-based method that can be with a W, for instance, but it doesn't matter. We need to pair this method with an estimate of the action value function. Okay, but the important part of this algorithm is the fact that you take the sum of the value of the actions over all actions. Accordingly, this method is called the all action method, or what you are writing now is the all actions update rule. Okay, first look at this remark. Every time we instantiate the stochastic gradient algorithm using updates given by this expected value, we have a new update rule and the new policy gradient algorithm. Okay, this is the first algorithm that you meet with policy learning, but it is not the most important one. It is promising, it is deserving more attention and study, but it is not the algorithm we are interested in this moment. I just want to share with you, yes, please. You're asking something?
No, sorry, I just activated the microphone by error.
Okay, I just want to show you a paper studying this, maybe this one. Yes, this is a paper studying this method. It is from 2018. Consider that this method appeared in 98 in the first edition of the book of Sutton, where he said, okay, this is a method that is worth more studying. And in 2018, somebody started studying this method. Here is called mean actor critic, showing you that this is an actor critic method. And I'm not sure. Yes, I have put this in the share in a folder called interesting papers, not must be known papers, but I suggest you read it. It's very nice, very light, and give you some light on this method. Actually, if you want to do something that could be also a small research paper, you could just develop the protocol for an experiment testing how good this method is. Okay. But we are interested in something different, which is the reinforced algorithm. This is the most well-known policy gradient algorithm. Usually when somebody says I'm using policy gradient, if he doesn't say anything else, probably means this algorithm. And this algorithm, you see, follows the same overall strategy. We have the expectation here, and we rewrite this expectation in a completely different way. And now we use as an update rule for the stochastic gradient descent just one single sample from this expectation. Can you see the big picture, the overall strategy? I mean, this is not important. The details, you can find them in the book. Okay, but just try to follow what I'm saying about this overall strategy of rewriting things as expectations and sampling them by just one single sample to use in the stochastic gradient descent rule. This is called instantiating the stochastic gradient descent algorithm, feeding the stochastic gradient descent algorithm with new targets. Remember, I started in the first lecture telling you, remember the word target is very important because in function approximation, we will use this language. Everything will be done using targets, targets, and targets. You get a target, you get a new algorithm. That can be good or bad. Now we have something called...
Just to be clear here, the G of T is just a way of estimating Q, right? For example, with, I think then the total reward if the notation is the same. Or
Exactly. Here you have Q, and you notice that I'm putting G. Of course, they are not the same, but in terms of expectations, yes, they are the same. And so in some sense, this is just an estimate of the Q value. Perfect. Very good. So I was saying that this is very common. I mean, it is called the reinforced trick because you use it in the reinforced algorithm. It is called also the log likelihood trick because you use it in the log likelihood computation. It is called also score function trick. I don't know very well from where this terminology comes from. And okay, this is obvious. And
I mean, because the score function is exactly the log likelihood function.
Oh, yes, it's another name. Okay, so this is the reason. Thank you. And the last equivalence is just due to the fact that if you take the state, take the action A, and then go on following the policy, what you're obtaining is just the return from the state ST. And so this is just an estimate of the Q value, exactly. Okay. Please notice also this. There is a very appealing geometrical meaning of this update rule. We are moving in the direction of the gradient, of course, because we want to improve the performance. And we are moving as much as the return, meaning that if the return is big, we are moving of a large step. Otherwise, we are moving of a small step. It makes sense, right? If the estimated return is high, then we think that direction is good, and so we want to move with a large step. But on the opposite, at the denominator, you have the value of the action. Not the value, sorry, you have the probability of the action. Why this makes sense? It makes sense because otherwise we would be counting more actions that are appearing often. Instead, in this way, if an action is appearing twice, then there will be a factor at the denominator counting that, and I will count every action in the same way. Okay, so this is sort of a geometrical meaning of this update rule that makes it very, very nice, I think. Okay. So this is called the reinforce algorithm. Reinforce comes from, maybe I can write this acronym because it was very hard to find this answer. If you are asking what is the word reinforce for, it is this: reward increment equal non-negative factor times offset reinforcement times characteristic eligibility. Please don't ask more because I have no idea of the complete meaning. But anyway, this is R I N, I guess the factor offset reinforcement characteristic eligibility. Okay, this is the weirdest acronym I've ever found, by the way. Okay, let me check the time. Just a moment, I'm checking what else we are going to. Okay, we are almost here. So I can tell you also this thing. I want to show you, not because it is important to derive it in another way, but it is important that the argument. So you can see that the same result can come with different strategies. I want to prove again the reinforce algorithm, the policy gradient theorem, if you want. And I will do this way. I have taken it from a book that I want to show you, that is here. This is a book from last year, and in particular, these names are very authoritative. So I tried to read this book. It's much more technical than the Sutton and Bartow, but here you can find the proof, the details for proofs, and so on. So. And what I'm going to show you is the proof of the policy gradient theorem given in this book. That is the following. Let's try to do it quick. It's actually quite easy, much easier, I would say, than the other one. This is the gradient of the value of the state. Now, we are writing the value of the state in a completely different way. Up to now, we were stressing out the fact that the value of the state is the sum of is the expected value of the sum of the return. Actually, it's in this sense, it's exactly the same thing. But what I mean is that I will use this notation. I will write the return as g of tau. Tau is an episode. Okay, and I will take the sum over every episode of the return of the episode times the probability of the episode. Okay, so this is just a rewriting of the expectation, the definition of the value of the state. Of course, the episode is starting from S0, is taking action A0 and going on, and the action is taken from the policy we are we are evaluating, and S0, if you like, is taken from an initial distribution. For us, S0 is fixed. And so this gradient is simply the sum over the episode of the return times the gradient of the probability of the episode, because only in the probability we have the policy. And this means that I can write this with the log trick, if you like, the sum over the episodes of the return of the episode times the probability of the episode times the derivative of the logarithm of the probability of the episode. Okay, but now the episode is this one, and the probability of the episode is the probability of the first state, S0, which is fixed, so no probability, times the probability of choosing A0 from S0, so the probability is the policy, times the probability of going in S prime, in S1, sorry, starting from S0 with action A0 and so on. Can you see what I want to say is that now I'm taking the logarithm of a product of probability, of a joint probability in some sense. And so all of this, I can replace all of this to be quicker with the product of the probability of choosing AT from the state as T times the probability of going into the next state once I started in state as T with the action AT. And I have to take the product for T starting from 0 to infinity. Okay. And then for the nice properties of logarithm, I can write the probability of tau times the sum from t.0 to infinity of nabla, the derivative of the logarithm of the policy, at times st, because in the model there is not dependence on the parameter. Okay, so here something magical happens, that the model, we are in the model free case, so we were looking for this. Actually the model is disappearing. Okay, and at the end this is just the expected value of what? Of the episode taken from the probability of the episodes, the expected value of what? Of the episode times the sum from t going from 0 to infinity of this nabla log pi at s t. Okay. Now, this is a derivation of the policy gradient theorem coming just from different ways. I mean, not going through the all action methods that we have seen before. If you think we are not making an unrolling, we are not plugging recursively a definition, because we are not using the Bellman equation, if you want. if you go back to the unrolling argument, we were using a Bellman equation, which is the recursive part of the Markov decision process. While here we are just taking a more direct definition of value of a state, non-recursive, if you like. Okay. So just to understand that this is still as in the beginning, as in lecture 1, this gives you an algorithm of few lines that is more or less the same. You generate an episode, you follow the steps of the episode. For every step you memorize the return you obtain from that step. The total return, you see, you go up to the end. So this is a Monte Carlo method. And then you use this this target, this total return you obtain, the sample of the value of the state, times the logarithmic derivative of the policy according to the gradient, the policy gradient theorem. And you see this algorithm, it works because this is a true gradient method. This is the sample from an estimate, an unbiased estimate of the gradient, because it's Monte Carlo, okay? So no bias. So it will converge to a local minimum, of course, with the usual stochastic approximation theory hypothesis. That means that this is in L2, but not in L1 as usual. Okay, and of course, as every method of this kind will converge very slowly. And since it is a Monte Carlo method, you need to finish the episodes to get the sample of the estimate. And this means that if the episodes are very long, they can be also 1,000 steps in certain environments, then this will take a long time. But anyway, this is the starting point for every algorithm, for every policy gradient algorithm. Okay. So in a few minutes, we are taking a break before passing to the other paper, okay? But for the moment, I want just to show you something. Skipping, this is a graph showing you how much is working on the short corridor or before the reinforced algorithm. And here you can see that according to different learning rates, you obtain different performances. Choosing a good learning rate for the policy gradient for every algorithm, but for the policy gradient for the reinforced algorithm is quite difficult. I mean, it's very sensitive to the choice of the learning rate, as you can see from the blue and the red graph. But what I want to tell you is the fact that despite the fact that this is a Monte Carlo method, and as such, it has a very high variance as usual, but we can reduce the variance with something which is called the baseline. The baseline is a standard technique in this kind of method, so you should remember it. When you have the estimation of the, in this case, of the Q value given by the Monte Carlo sample, then you can diminish the variance of all the Monte Carlo steps, subtracting a quantity which is dependent on the state. And so what does it mean? Instead of giving you the general theory, assume what it usually is, that this quantity dependent from the state is an estimate of the value of the state with respect to the same policy you are evaluating, okay? Now, remember that this was an estimate of the Q value, okay? Or just think that this is the Monte Carlo return. Why the Monte Carlo return is so such a high variance? Because it accumulates the variance along all the steps, many steps. high variance. I know I already told you several times, but never mind. Now you are subtracting the value of the state, which is in some sense, on average, going through the same many steps. Okay, so in some sense, what remains here is more or less just the first step. Remember, this was the action value estimates, actually. So the first action is fixed. Anyway, you are subtracting the baseline. What I mean is that qualitatively, you are reducing the number of steps. And so reducing the variance. Well, in general, subtracting the quantity, the variance can decrease. It depends on the quantity, of course. But if you choose wisely this quantity, this baseline, this is called the baseline, and usually what you choose is just a value function, then you can dramatically improve the performance, the convergence speed of the algorithm. You can see here, this was the best result obtained before without baseline. And using a baseline, you skyrocket this way. You reach convergence in no time. Okay. Now, I told you that we can replace the estimate of the Q value that we sampled with the Monte Carlo return, but we can sample that estimate also with a one-step return. Remember, this is a notation for the TD0 return, one-step return. Okay, and this gives you another algorithm. And okay, so this was the slide that I used to tell you what is an actor-critic method, but just realized I already told you what it is an actor-critic method. In this case, you can see that we are evaluating the gradient of the policy. The policy is the actor. We are going in the direction of the gradient of the policy. So we want to follow what the actor wants. But here there is a critic that will change the step size in some sense, and in some sense will refrain the actor from going too forward in this direction, following his ideas, once the estimated return is small. Okay, if the critic is stating that what the actor is doing is false, then it will refrain him from going in that direction too much. And this is synthesized from this nice picture that I clearly have stolen from another course that is strongly suggested because it is very nice, where in an actor-critic method in a Tetris game, the actor wants to rotate the piece, but the critic computes the value of this action, understanding that the value is low, that the action is bad, and then states really bad action, don't do this all the way. Okay, just to have some color and some nice picture. And this is the last slide before the pause. So this is a summary of all the policy gradient methods we can have. Remember, from the beginning, we started from an estimate of this kind, from a rewriting of the gradient of the performance of the policy in this way, as an expectation over a policy gradient argument. When I say policy gradient, I mean that there is the logarithmic derivative of the policy. And then we started taking different estimates of this that originally was the all action value. The first estimate is the reinforce, where the estimate is a Monte Carlo one. This is unbiased, so it is a true stochastic gradient descent method. And otherwise, I can take the Q value. I can take the advantage that I haven't told you what it is, but I should. Well, the advantage is when I use the baseline, I take the Q value of ST of this action and I subtract the value of the state. This is called the advantage of the action, because if you think about it, this is the average value that you can have using the action in the state. And this is one certain action doing something. So according to this value being positive or negative, it means respectively that I'm doing better or worse than the average. And this is called advantage, and you will find pervasively in every algorithm this terminology also in the next hour. And then we have methods which are on one step, n step, or TD lambda, which we haven't said anything about. Okay, so everybody, this concludes the lecture number 4, but I mean the slides number 4. Yeah, we have just the exercise page. And I will do, let's say 9, be generous, 9 minutes pause, okay? It's 4:01. Let's get back at 4:10. I have at least 2 coffees in the meanwhile, because the next part of the lecture will be much more difficult. Sorry. Well, will be fun. I mean, we will try to read a very highly influencing paper with almost 3,000 citations. It's a very famous algorithm called the Trust Region Policy Optimization, and it is a policy learning method. So you will be surprised that you are now able to, let's say, understand a very, very difficult paper. So questions are welcomed. Otherwise, we are going for a coffee.
Okay.
So okay, I think we can start again with the last part of the last lecture.
Okay, thank you, Luigi. So remember the big picture, the structure of the course. We started with value-based methods, that is methods learning a value function and using the value function as a proxy to obtain improvements for a policy, with the aim, the final aim, to find the one optimal policy. And then today we started looking for methods that don't use values, but just try finding the optimal policy. And of course, this method starts with parameterizing the policy, simply as that. Okay. Now we have looked at this. The methods learning the policy have a good theoretical ground given by this policy gradient theorem. If you didn't notice, this policy gradient theorem means that we can follow exactly the gradient of the objective function. Following exactly the gradient of the objective function means that we are really going in the true direction, in the stochastic, in the gradient descent direction. And this is good, usually. Okay. As you have seen in the last slide, we can do policy learning. We can learn a policy starting from the policy gradient theorem in several different ways. And now we are looking for another way, which is very, very different. It's actually not using the policy gradient theorem, but it is anyway a policy learning method. Before starting, I want to show you, maybe not here. Not here. Sorry. Let's do this. Okay, this is on the archive, the paper we are going to read, and I just wanted to show you this line. Okay, so this is a very high influential paper. This is one of the most widely used algorithm when you're trying to learn a policy directly. Actually, a related one called the proximal policy optimization algorithm is used, just to give you another motivation. So I guess you can read the text. And that's the other time I just highlighted the parts that I want to read with you. And I invite you to think about if you're really understanding at least the idea, what there is, what is the meaning of the sentences. Okay, first we start with describing an iterative procedure for optimizing policies. This is clear. We are optimizing directly policies, not values. And this procedure we are describing will have a guarantee of monotonic improvement. Remember that with function approximation, we lost the policy improvement theorem. So we lost the fact that when we improve a policy, the new policy is actually an improvement, okay? In this case, they are developing conditions to give theoretically, in some sense, a policy improvement theorem, okay, in the setting of policy learning. So it starts very well, I mean, it seems very important. Then look at the other sentence, typical of this kind of papers. After that, by making several approximations to this theoretical justified procedure, we develop a practical algorithm. Read in another way, okay, the theoretically procedure we describe is not really, cannot really be used, is theory, okay? We then, in the next part of the paper, we develop making several approximations. That means invalidating, in some sense, the theoretically grounded arguments that we were using. We develop a theory that can be used. Okay, this is typical, and it is the way to do this kind of thing. You do some theory, but then you can't follow that theory because that theory is using quantities that you can't compute. Then you write that quantities as expected values and you sample the quantities. Overall strategy, as I say. Okay, and at the end, of course, they had to say that despite these approximations that deviate from the theory, the algorithm works. Where working for an algorithm means it is able to solve different families of problems in a very good and efficient way, probably above a baseline. Compared with the usual solution of this kind of problems, our method works better. Okay, now look at this sentence. Algorithms for policy optimization can be classified into three broad categories. One, policy iteration methods. Piece of cake now, okay? I will not comment on this. It was lecture 1 and lecture 2. Policy gradient methods. Now you know what these are. And now you discover that there are a third family of methods called derivative-free optimization methods. And here you understand that the policy gradient methods are using the derivative, right? There is the policy gradient, they are using the gradient. Well, there are derivative-free optimization methods. And in the following, they say, in general, derivative-free stochastic optimization methods are preferred on many problems. They work very well, they are saying. Okay, they do some example and so on. And the fact that the gradient-based methods aren't able to consistently beat gradient-free random search is unsatisfying, of course. Also because continuous gradient-based optimization methods has been very successful in the supervised learning tasks, meaning not in the reinforcement learning, okay, with huge number of parameters. And if we were able to extend their success to reinforcement learning, this would allow for a big success, okay, efficient training, very complex, powerful policies. I mean, if you can train complex policies, that means tautologically that we can solve complex problems, not tautologically, but I mean, we can hope for this. And this also means, briefly, they are saying that if we try now with actual naive policy learning methods, the methods that I described in the slides are, despite maybe the lecture was a little bit complex, more complex than the other lectures, but that methods are naive methods, okay? If you want really to apply them, you have to refine them very accurately. So briefly, naive policy learning is not efficient. In this article, we first prove that we can minimize a surrogate objective function. Remember, we are approximating things. We have an objective function. Here they talk about a surrogate. This is a technical term in the minorization maximization methods. But anyway, this means in particular that they are not minimizing the objective function, but a surrogate. And they prove that minimizing this surrogate guarantees a policy improvement with non-trivial step size. This is something also, maybe I can just for a moment do this. When you do the gradient descent, when you follow the gradient, you know that this is the gradient in the direction of a maximal ascent, maybe. And then you follow the gradient means you go in this direction for a certain step size. Okay, you have no guarantees on the fact that you are not choosing a too large step size. Maybe this is too big. Too big means that, okay, now I'm going up, but I was here, I followed a step size long this way, and now I am here, much lower than before. Okay, and when you follow a naive gradient method, you have usually this problem. You have only local guarantee of improvement, and not, you can say, I can go as far as possible or something like this. Okay, we'll be more precise here. So this is a problem of the gradient methods in general. And this is the meaning of these non-trivial step sizes, okay? So they say, when we use the gradient, we would like to make non-trivial step sizes, meaning we would like to make informed steps in some sense. And then this is a theoretical argument, a theory, and then we make a series of approximation to this theoretically justified algorithm holding a practical algorithm. Okay, so this is the general procedure. First the theory, then from the theory the theoretical algorithm, and then from the theoretical algorithm the approximated algorithm, and then the experiments. In our experiments, we show that everything works. Okay, so this is the introduction. ask, please. Now we are reading carefully all the preliminaries. Okay, so I'm just talking, I'm explaining here, but please stop me if you don't understand. We're not going to finish this paper, okay? So we can stop wherever we like. So, consider an infinite horizon discounted Markov decision process. What it is this? Well, you know now what is a Markov decision process. Discounted meaning that they are using a discount. I don't remember I told you about this definition because it is not the one used by Sutton and Bartow, but this means simply that, I mean, doesn't mean not episodic, can be episodic. It just means that you don't have a fixed length of episodes. Okay, infinite horizon is a different classification for MDP, means that the trajectories can be infinite length. So can be episodic or not. It's in opposition with finite horizon. Well, you have states, action, transition, reward, initial distributions, okay, and discount factor. Here, all the details. Please notice that the transitions are not the joint probability of the states and rewards, but here the rewards are taken apart. The reward function is here, and it assumes that there is only one reward per triple state action next state. This was a question actually in the very beginning of the course. Some of you asked if the reward was actually determined by these data. Usually it is, so often that sometimes the MDP is just defined this way, but the way I have defined includes also the multi-armed bandit as a case, so it's more general, okay? But in this case, we're assuming, let's say, a deterministic reward. And well, this should be, I wrote the comment piece of cake now. I mean, this is just the first hour lecture. Now, R is the reward function. This is the distribution of the initial state. If you like, you can think about the fixed initial state, okay? And gamma is the discount factor. Now, from the fact that is not considering gamma equal to 1, then you can guess that probably is excluding the episodic case. Because in episodic case, usually you have the reward factor, the discount factor, sorry, equal to 1. Okay, now, let pi denote a stochastic policy. No problem, okay? The stochastic policy is giving okay. No, I'm pausing because I don't understand this way of representing the policy. Okay, think about the stochastic policy, and as usual, consider is expected discounted reward. Okay, and this is the value of the policy. This is what we called J. Okay, so this is the value of the policy. The value of the policy is just the sum of the reward. So this is the total return. Please stop me if you don't understand. This is the total return, and this is the expected total return. So in other terms, since here you're taking the initial state from the initial distribution, this is what we called previously the value of S0 for pi theta, with the difference that now we have also a dependence of S0 from the initial distribution. So you can say this is the expected value where S0 is taken from the initial distribution. okay, which is the J that we were talking before about. Okay, and being the J of before, of course, if you take its gradient, you have the classical policy gradient reinforced algorithm, which is very unstable and not efficient. For this reason, in this paper, they try to improve it. In order to show you that the reinforce is very unstable and can be not efficient, you've taken an example from a paper from 2002 in this page. Okay, you see number 1 was the annotation. It's a paper of Kakade in 2002. This is figure 3.1. I think I put the paper in the shared folder. Now, this is a very simple grid word. This agent can go right or left, but he has available 3 actions, not 2. 2 of them goes on the left and only 1 goes on the right. Okay. And the policy is choosing between the 3 actions in the uniform way. Well, if you make a computation on a length and states grid line, say, you can compute the average time to reach the goal, which is the state label 1. The average time to reach this state from the starting state S, due to this asymmetry of having 2 actions over 3 actions going in the wrong direction, let's say, this time is given this way. In particular, it is exponential in the length of the grid word. Exponential for an algorithm means very, very bad. And this is just an example of a toy problem. If you think this is a toy problem, it's not a real problem. The traditional policy gradient method, the naive policy gradient method, the policy gradient, the reinforcing method algorithm is not working well. Okay. Okay, so when in this annotation you find a number, means that there is something somewhere. Okay, so this is the usual objective function that we want to maximize. Now, we will use the following standard definitions of the state action value function. So in this paper, the state action value function is capital Q, the value function is capital V. These are the true value functions, okay? And the advantage function is capital A. Well, the value function of the action is the expected value. You can see the difference from before. I'm not choosing AT. I'm starting from ST plus 1. So the expectation as a fixed action. So this is the classical Q value, or in our terminology. If you look here, this is exactly the same. You see that the argument of the expectation is always the same. It's just the difference on which you take the samples, on which you make the expectation. Here you consider also the first chosen action in the to make the expectation. So you are changing the probability distribution of these rewards. Okay, and this the new thing that I just told you at the end of the last lecture. This is called the advantage. That means on average, your action, the action you are computing the advantage of, how much better or worse is with respect to the average value of the state in which you're taking that action. Okay, please notice that in a research paper, they are always very precise on from which distributions they are going to choose actions and so on. In particular, in a paper where you are improving a policy, at a certain moment, you will have an old policy and a new policy that you improved. And so it is essential that it is always very clear from where you are picking up the actions. If you remember the Q-learning algorithm, there was a target where an update rule where one action was taken from the original policy and the next action was taken from the max policy. If you remember, it was an off-policy method, so using behavior and target policy, different policies for choosing the actions. Okay, let's go on, assuming you don't have questions up to now. Now this sentence. And now we start trusting a little bit the paper. The following usable identity expresses the expected return of another policy, pi tilde, in terms of the advantage over pi accumulated over time steps. If you want the proof of this, you can see here, oh, this is the Kakade paper with the example I have shown you before. Or you can also just check the appendix. The paper is more or less self-contained. Several things are, several needed proof are contained in the paper. But what I want to say here to go on is that this is a convincing formula. I mean, just have a look at that. What is this? The advantage is just the one-step action value in some sense. You see, here you have the Q value of the action. The Q value of the action takes this action and then goes on up to the end. But when you take out the value, you are just leaving the single reward obtained with a single action. Not really, because you are subtracting the average reward also from that reward, but essentially you are just taking one single reward. You are removing every other reward. I'm not sure I'm clear, but the idea is that this is just one single reward, and this is the sum of just one single reward discounted. So this is just a return. This is the total return, but the actions are taken by pi tilde. So this is the total return pi tilde, the total return of given by pi tilde. That means this value minus this part, because you are removing the value from the advantage. Okay, the advantage is the Q value of the action minus this part. And so this means that you are removing this, which is crossing out with this. So this is going out with this. And what remains is the sum of single rewards with actions taken with the trajectory followed by pi tilde. That is the value of pi tilde. Okay, so this is not a proof. Probably can be evolved in a proof, but I mean, it is convincing, at least. Why do we need such an equation? Well, because remember that in few lines, we are going to control the changes of an old policy to the new policy. And so we need to check how the performance is changing. If the old performance was this, how much is the new performance? Well, we just need to add this term according to this formula. So this is needed to control how the policy changes when going from the old value up to the new value. Okay, now let rho pi be the unnormalized discounted visitation frequencies. Now you also understand why they are saying unnormalized, because we already met the visitation frequencies without discount, but we already met the probability of going from S0 to S, the probability of going from S1 to S, and so on. And you notice that in a certain moment we used to discount that part. And the discounted visitation frequencies, what were called the policy distribution, right? So this is more or less the policy distribution, but without discount, without normalization. Okay, and now we do so this one again. The starting state followed the starting distribution, and the actions are chosen still according to the original policy pi. Rewrite equations 1. Instead of summing over time steps, we can sum over states. You understand, this is something that you can always do. You follow a trajectory like here, and you can say that you are just checking state by state which state you can reach from the previous state. And so that one is measuring the probability of the trajectory up to that moment. So if you do this in this equation, now we are a little bit tired, but trust me that if you use this equation and you follow the steps, you can follow it. Okay, let's try just the first line. This is the same. Okay, so this is done. And then this expectation is taken with sums. I mean, I start here from S0, right? So I take the sum from t equal to 0. So the first state will be S0. And I want S0 to be a certain S, because here I'm taking S0 every possible initial state. So here I'm taking S0 equal to S. S is every possible initial state, okay? And so I take the sum over every state. Of course, when here there is S0, this probability is the initial distribution of states, because this is the meaning of S0, and so on. When I'm taking S1, then what will enter is the probability of S1 to be S, and so on. Okay, following this is the joint probability of going of arriving in S, and then in the state S choosing the action A. At that point, you are in state S, you have chosen action A, and so you are taking the advantage, this one, the one of which you are taking the expectation. And so you are weighting this advantage with the probabilities. And once you sum over every state, every action, and every possible time step, you are just doing this expectation. Okay, I don't know if this is clear, but it should be. Then you make some algebra on this, and you obtain this expression. Well, remember, this is sort of what we already did in the policy gradient theorem, in the derivation of the policy gradient theorem. We are isolating the sum over all steps. This is the probability of starting from a state and going to another, the probability of starting from the probability of that the state at time t is a certain state S, summed over all the time. So this is the probability that at any time, the sum is the probability that at any set time we reach the state S. Okay, so you understand this is related to how many times the state is visited under the policy. And observe that now the policy is pi star, because we use equation 1 where we obtain pi star. Okay, so here the expectation is made sampling actions from pi star. Okay. Now, look at this. Look at this equation number 2. And imagine that you are in a situation where you can say that this term is always positive. If you can say that this term is always positive for every state, I'm summing over all the actions, so this is dependent on the state, then since this is a number, these are unnormalized frequencies, these are positive numbers, these are sum of probabilities, and you can say that certainly the policy pi tilde is improving with respect to pi. Remember, these are the performances. So this is this plus number that under this hypothesis, you can say it is positive. And so you can say that this is bigger than this. So this equation implies that any policy update that has a non-negative expected advantage at every state, that is the condition that I wrote, then is going to increase the policy performance. For sure. Okay, this is the theoretical guarantee we were talking about before. Actually, not yet. This is something that you already know. In the tabular case, this is just the policy improvement theorem. Just, I mean, now probably you don't remember by memory the policy improvement theorem hypothesis, but if you go to the policy improvement theorem and check the hypothesis, you will find that if the condition QSA is greater than the value of the state S, then the policy improves. This condition reads, now that you know what it is, the advantage is just the Q value minus the value. This condition means that the advantage of SA is greater or equal to 0. Okay, and the policy improvement theorem was in the deterministic case. So this sum over all the action times the probability of the action is just concentrating over the only action you can choose from the state S. And so this condition, this to be greater or equal to 0 for every state, read just like the policy improvement theorem. And so this is another, if you want, this is another very sophisticated proof of the policy improvement theorem. Okay. And in fact, they precise, this implies the classic result that the update performed by exact policy iteration, which uses the deterministic policy argmax, improves the policy. Okay, and this is the theorem. And zero state visitation probability and so on. However, very important sentence, in the approximate setting, it will typically be unavoidable. You can't avoid this due to estimation and approximation error, that there will be some states for which the expected advantage is negative. Okay, it's the same as I was telling you in the last lecture for function approximation. When you update a parameter, some state will improve and some other state will not improve. Okay, this is another formulation of this sentence. So somewhere you will have this less than 0. And okay, you can say, very well, I have I have this equation too. Okay, let me erase this part. I will give you the original annotated file, don't worry. So if you can take this equation and you can say, okay, I can optimize this equation. I mean, I can find the parameter values such that pi tilde, which is the new policy, which is the policy given by the updated parameter, makes this value as big as possible. Okay, so you can try to optimize this from this equation, but trying to optimize this equation is not going to be possible, because inside here you have the very complex dependencies of probabilities on probabilities. Okay, that is this sense. The complex dependencies of this from pi star makes equation 2 difficult to optimize directly. So what we are going to say, well, that is difficult because there is something that we can't control, that is the visitation frequency of the updated policy. And what if we substitute that expression with the visitation frequencies of the original policy? So here we write the same as equation 1, but simply we replace this from this. I mean, we replace this with this. If you have a look, I will show you again the equation 2. Let me try. Okay, you can see equation 2 and you can see equation 3. Okay, it's exactly the same. Okay, I just removed the dependency from pi tilde here. Can you still read the text, this dimension? Maybe I can leave this way.
Yes.
Yes.
Okay. So note now that this new linear approximation, not linear, this new approximation uses the visitation frequency with respect to pi instead of pi tilde. That means that it is ignoring changes in state visitation density due to changes in the policy. You should be able now, at least qualitatively, to understand these sentences, okay? When the policy is changing, there are changes in state visitation density, because how many times I visit a state depends on my policy. Of course, also from the model, but the model is fixed, we are ignoring it, okay? However, there is a very, very good news, guys. When the policy is parameterized, as it will be, by a differentiable function, then what is written in equation 3 is a first order approximation of equation 2. What does it mean? It means that for any policy, representable policy, that is for any parameter value theta 0, if you take the value in theta 0 of L, this is the value of that policy. By definition, what it is this? Okay, see, yes, this is just by definition. And if you take the gradient of this computed in theta 0, this is exactly the gradient of the performance of the policy. So you see, this is the same value. This is the same as the performance of the policy for any policy, and the derivative is the same as the derivative of the performance of the policy in this point. Okay, so this is a first order approximation. It's a good starting point, okay, because this is something we can't optimize, and now we have found the first order approximation, something which we hope we will modify in order to be a little bit more usable and computable and so on. And so equation 4, particularly these two equations, implies that a sufficiently small step going from a policy to a new one is a sufficiently small step that improves this will improve also the performance. Okay, because this is a first order approximation. But as I told you before, this doesn't give any guidance for us on how big a step we can take with this gradient algorithm. This is the same as before. I can start showing you this picture maybe. You see here, if I have, this is the performance. Okay, and let's say it is not yet, but let's say this is a first order approximation, tangent in the point and passing through this point. I mean, if I improve this, locally I can say that I'm improving also this. But as soon as I'm out of this, maybe the approximating curve is going over the other curve. Okay, I have no idea of how much big a step I can take in order to continue improving the performance. And remember, this is what I want to do. I would like to take as big a step as possible in order to increase the convergence speed. Okay. So to address this issue, in this paper, these authors proposed a method called conservative policy iteration, for which they could provide explicit lower bounds on the improvement. Explicit lower bounds meaning that there will be at least this improvement for the policy. Okay, this is a big result. In order to do this, they say, okay, you take the greedy policy. Okay, you start from a policy, or from now on, let's say we have a policy, we call the policy pi old, and we want to improve pi old, the performance of pi old. Okay, and since the performance is approximated by L, we want to improve L pi old. Okay, so let's say we take, with respect to L pi old, the best policy possible. That is the argmax between every policy of L pi old or pi prime. That is the performance of pi prime, the first approximation, the performance of pi prime, and we choose the pi prime which gives the best approximate, the best result here. You understand that pi prime is the best policy you can have. Okay, now could be too much. Pi prime is certainly an improvement of this, but could be too much for the original performance. So you need to make some more conservative. So the idea in this paper was just take this convex sum of the best improvement you can have plus the original policy. If you take any policy in this family, this is a segment of policies, right? You can choose this alpha, and you have a new alpha, a new policy that you call policy new. This is called the conservative update. whatever policy nu you take in this family, we have very, very good news. We have this bound. What does it mean, this bound? This bound means something very important. I mean, I don't care what it is this, I don't care what it is this. Okay, just think about the fact that this is a bound on the performance. This is the true performance, not the approximated performance. The true performance of the policy nu, the policy that I want to improve, will be greater or equal to this, but this is certainly positive, and so this is I mean, this is an improvement. This is a lower bound on the improvement. According, I mean, in order to have this, pi nu must be in this family. Okay, so this means that if pi nu improves the second side, then it is an improvement also for the first side. Okay, and this is an argument called the minorized maximization that it is worth to be said before maybe stopping the lessons, the lecture, and it is this one. This is a common argument in optimization theory, so I apologize if some of you already knows this kind of argument called the minorized maximize methods of this family. It's a the idea is the following. Imagine you have a function that you want to maximize. Okay, in this picture, the function we want to maximize is a function of policies, but just think of this as x and y. Okay, and imagine you can find in a point, for every point of your domain, you can find another function, usually much simpler to optimize, typically a second order function. Imagine you can find another function which is completely below this one. Okay, so it is not going this way, it's completely below. You have a global optimization statement, something like this. Okay, which is what it happens. And of course, you want this to be an approximation. So here you need the minorized function to be tangent to the original function. Now, how can you maximize in an optimal way with respect to this data your function? Just do this. Take this point. I told you that the green function is simpler than the other functions, so you can probably find the optimum of this function. Find it. Have you found this one? Okay. Take the value. This is pi nu. And take this. And now build another minorized function, another surrogate function. This is the famous surrogate function. Okay. And take, I don't know, maybe this one. And now we are almost at the top, so I can draw a good picture. And optimize the picture below. And then you take this and you see in 2 steps here, we reach the maximum. Okay, this kind of methods relies on the hypothesis that you can build this surrogate function in every point of your function, and that the surrogate function is easier to maximize. This is a family of methods called minorize, maximize, and methods. Okay, and so what they said here is we can apply this kind of optimization methods in order to find the maximum. And this will give eventually an update rule, but we are almost finishing the lecture, so we are not arriving to this. But I just want to point out that this was done in 2002, and it is very, very limited because it doesn't hold for every policy, but just for a conservative update. Just if you take the policy you are improving, if you take the improvement just in a small family, in a one-dimensional family of policies. What they did, and it is written here. Our principal theoretical result is that the policy improvement bound in equation 6 can be extended to general stochastic policies. So they were able to derive again a similar bound for generic stochastic policies rather than just mixture policies. Okay, and this is the new bound. You can see a very similar. Of course, the symbols have a different meaning. And here something very nice appears a distance between the old distribution, old policy, and the new policy. And this distance will be eventually related to the KL divergence, linking this paper, the techniques of this paper, with something called information geometry. And I think this is a good point to stop. I mean, there are a lot of annotations here, but we would probably need another hour at least to finish this part. Okay. Thank you, everybody.
Thank you very much, Maurizio. And are there any questions?
Thank you very much.
So, thank you very much for a very nice and interesting course. And I was wondering, it would be interesting research directions to take for the future. We have seen what has been so far, but it would be interesting to develop from a mathematical point of view.
Say it again, because there is some background noise. You are asking for research perspectives in reinforcement learning, or more in general?
No, from a mathematical point of view.
Okay. Well, as you can see from this paper, it's very theoretical. I mean, there is a lot of mathematics. This is there are not so many papers this way in this field. They start proving theorems, giving theoretical guarantees. Okay, and after that they make the empirical part, which is, by the way, essential. I mean, if you just do the mathematics and you don't use that mathematics for something that improves over some old algorithm, something like this, probably is not as valuable as it could be. But for the moment, I would say a lot of research perspective for mathematicians in reinforcement learning is exactly in this field, the one of policy learning, because policy learning are relatively new actors in this field. And as you can see, they are promising from one sense, but very not efficient from several point of views. So there is a lot of research on this. For instance, the classical reinforce is very not sample efficient. And at the moment, I have a student that is preparing a paper exactly on this. There is a very recent paper on the archive studying the efficiency, how to improve efficiency on the reinforce method. And the other part, I would say, is the explainability part, but this is a long story and not particularly related to reinforcement learning. So probably is not what you were asking for. And also another field is the field of the natural policy gradients. The one I was citing before, it is called information geometry. This is a very, very appealing research topic, which involves metrics in spaces of probability distributions. So it is mixing geometry and probability. So for something like me, I'm born as a differential geometer and now doing probability. So it's very appealing. And this is there is a sentence here at the end of the annotations. Yes, keywords here on the right side. The keyword to understand this part are information geometry, Fisher metric. Maybe you have heard this word, and natural gradient. I don't know if this answers your question.
Yes, thank you.
I have also more a comment. I would like to ask you then a question. First of all, thank you for the course. It was very inspiring. And my question is about the fact that we discussed, as in all the literature here, the model-free versions of reinforcement learning. But there is really very few papers that talk about model-based. And, you know, since humans are basically model-based learner, I mean, we have a model of the world and we act, we use, we perform our policies based on models. Would you like to comment this? I mean, and also about future direction. If you think that the really good pathway of the future of reinforcement learning will depend also on this.
Well, that's a very interesting claim. You say that humans are model-based.
Actually, I forget to tell, I'm a cognitive scientist.
Okay.
I work on this, so.
Okay.
And there are a lot of papers that actually study how much humans use model-based versus model-free. So of course we use model-free, but mainly we act on the environment using by firstly creating models. This is our first attempt. Even animals, I mean, not just humans.
Okay, so that's perfect. So I completely agree with you. So for the other people listening to this, there is two meanings of the word model-based. What I told you was the environment as a model, and in the first lecture we were aware of that model, right? So we know the ground truth. We know what it is really happening in the world. And this is what we have called model-based. But actually, the more common use of this word means that we don't know the model, of course, because usually we don't know the model. But doing experience, we learn a model of the model in some sense. We learn some approximation of the model. And then we start acting according to this approximation of the model. In reinforcement learning, a method doing this, that means first learning an unknown model, so starting with model free, but then learning an approximation of the model, and then using that model, that means that learned probabilities, to use model-based techniques. These kind of methods are called model-based. Okay, and so there is an ambiguity in the term model-based reinforcement learning. In this second family lives the most promising algorithms in reinforcement learning. And in my opinion, this is the future of reinforcement learning. In particular, this is the future of the general artificial intelligence. That means some artificial intelligence that is able to enter a problem without knowing anything of the problem and learn something essential of that model, not only in terms of features, but in terms of rules, in terms of model, and then act optimally for that problem. And the general artificial intelligence must be able to do this for several models. So you see the layer of learning in this respect must be the model and not the actions or the policy. Because the policy is something you learn once you have a problem, what to do in this problem. But before learning what to do in this problem, you have to learn what is the problem. So once we have a system which is able to learn what is the problem and then learn what is the optimal policy for that problem, and this for several different problems, this will be the famous general artificial intelligence. In this respect, always in the Alphago family, there is the last evolution of Alphago, just recently published on Nature, of course, as usual. And this is a version of AlphaGo which is no more AlphaGo. It is no more alpha. It is called Mu0. Mu stay for models, because this method is able, this algorithm is able to learn without knowing the rules. So without knowing the problem, is able to learn how to play several different games. That is Go and chess. You could say, okay, but Go and chess are not so different. And for this reason, they inserted in the same algorithm, they tested the same algorithm on the Atari video games. And you, I guess you agree that chess and Go are completely different from Space Invaders. And this software was able to reach superhuman performance on every of these problems. Of course, this means that in the first steps of training, the algorithm is learning the model, okay, and then is using advanced technique to act optimally with respect to the learned model. So I guess my answer is that I agree with you. And also for reinforcement learning, the future is on model-based algorithms in this sense, not in the sense of the first lecture, I mean.
Okay, thank you so much.
Any other questions or remarks?
I have a curiosity if I can. Of course, different algorithms perform differently on problems. For some problems, we have some algorithms that provide better results, on others they work in a worse way. So what would you say that is a top application, a killer application for reinforcement learning? And where do you think that reinforcement learning cannot provide a solution that is at the same level of other forms of learning?
Say again the last sentence.
So where reinforcement learning works well, and where reinforcement learning, in which application reinforcement learning is not at the same level of other forms of learning.
Okay, of course my answer is a little biased, but I don't think, I mean, reinforcement learning beats every other technique. I mean, I'm not an, of course, I can say I'm an expert of reinforcement learning and not at all of machine learning in general. So this is not an authoritative answer, of course. And as I stated before, when you have a problem, if you can solve the problem with simple methods, you're welcome, you should do that. But if you don't, if I have a problem, I have no idea which is the technique to use to solve that problem, I use reinforcement learning 100%. And I'm pretty sure that there is some technique, not that I can find the technique to solve every problem, of course, but that there is a promising technique that is able to solve every problem. Of course, must be a decision problem, I mean. But there is a sort of a fundamental hypothesis in reinforcement learning. If you read the book, it is very fascinating. It is essentially stating that every problem can be stated in terms of a Markov decision process, of the decision process, with a certain reward. It is called the reward shaping, this topic. You can always shape a reward such that the maximization of that reward via reinforcement learning or via other techniques, but such that maximizing that reward, the cumulative reward, gives a solution to the problem. I'm not sure I answered.
Yes, I was just wondering about applications. So, we talked about games, but some real world application, what would be?
Real world, but well, this. Can I show you a video? Just one minute. Yes. Okay, so what I'm going to show you, can you see the video?
Yes.
Yes. Okay, this is a simulation made with the artificial environment. The environment is providing very accurate physical laws, and there is a humanoid. You can see this this object is a humanoid with certain degree of liberties, rules for moving the arms and legs and so on. And this started completely from scratch, moving the arms in a completely random way. It was trained by reinforcement learning, by a technique of policy learning, actually. I guess is sort of an advanced form of this trust region policy optimization. And this is the level it reached. So, okay, I mean, this is not a video game, okay? The application, this is robotics, if you think about it. This is the simulated environment, but from this you can go to a real environment. This is, I repeat, learned from scratch. No human previous knowledge was inserted. This is very funny, the way it's moving the arm. It's being pushed around now from this red. Goodbye. Okay. So, okay, that was a robotic application, if you think. Another thing I can think is the acrobatic flight of helicopter. This is this reinforcement learning is working very well. In automatic parking, of course, automatic driving. You know, the cars that are driving by themselves. That is reinforcement learning.
Just one observation and question about the last part that you are saying, and also about the example that you're making. Because of how it is and how it works, to apply this approach to a problem, you need to have a problem that is simulatable. I mean, because you have to make a lot of trial, and in some environment the trial means dead or means something not
okay. So if you understand the question, every method I told about probably needs a simulation environment. But remember, at a certain moment, for instance, I told you, what happens if you only have a limited amount of experience? What happens if the experience is costly? And I told you there are methods in this respect giving results. And so if your experience is costly, if you don't have a simulation environment typical for drugs experimentation and so on, then there are several methods that you can apply. Yes, but of course, this is a problem that should concern you. But let me check if I can find something to show, which is very nice. Learning. Oh, this one, I think it was. Okay, so this is a cart pole. You know what it is, this problem?
If I remember well, you want to have it on the upper side, so
exactly up. You have to swing it up. Perfect. So you see, this is not a simulation, okay? I mean, this is a real environment. Yeah. And as you can see, every episode takes seconds, or let's say 15 seconds and so on to replace. Okay, the experience is shorter, but, and this is trial number 3, no cheating. Nobody's driving, and you can see that everything is completely random. Of course, this algorithm is optimized to be very fast. And now that he has found the solution, everything will be easier, because he has reached the point where the reward was good. I guess this is just a simple temporal difference method with some tuning. Almost there. I mean, I'm excited when I see this, because it is really, you can see it's one object which is living. I mean, come on. This is a machine. Okay, so, and you see, it can also resist to outer. I mean, this is impressive, right? Yeah. Okay, so yes, the answer to your question is, of course, it is a very important point. In particular, if you want to use Monte Carlo methods that are very slow, you need a simulation environment. If you have a simulation environment, everything is simpler and easier. And but if you don't, there are methods that work anyway.
Thank you.
I have also a question about the research in this field. Do you think that this could be a good way for studying natural language processing?
Oh, well, yes, definitely. This is a brand new and brand hot topic, analyzing with reinforcement learning and natural language processing the sentiment. For instance, I have a student that is now studying these things in order to try to use the sentiment acquired with NLP analysis and reinforcement learning to forecast, to say what's happening on trends in the stock markets and so on. I mean, if you have news saying that a certain company has made something that was perceived as bad, and you can read this before the stock decrease its value in the stock market, then it is a good thing. I mean, yes, definitely. This is a very, very new topic. I would say of every topic I can think about, this is one that is terribly hard. I mean, using the natural language processing is so complex, so full of intricate relation, extracting features from it is so easy for us humans to make a mistake when we talk each other, to misunderstanding things that I can't imagine a computer can do this in an efficient way. But anyway, it is a research topic, yes.
Hi, sorry, just a question about the previous video. So there, the state space is essentially, what can it be? Maybe the angle of that bar. And in this case, I was thinking it would be continuous, and also was thinking at the reward as well. So differently from the case I think we've seen so far, where we have an episode there, like it's not just trying to reach the vertical position, but it's trying to keep it on for whatever time. So is there some kind of time continuity or that is going on in that reward, and as well in the space, in the state space, is it continuous, like the angle of
So what you're asking is how do you model, how do you write the MDP and the related reward in order for the theoretical solution to this MDP to solve the real problem, okay?
Exactly,
and of course, there is not a unique answer. You can do, for instance, when you have a continuous problem, you're right, this angle seems continuous, but you could, for instance, discretize it in for 1 degree, obtaining 360 states, right? And the actions can be push on the right and push on the left. But if you have a sophisticated card, the action can be also push on the right with this power, push on the right with twice the same power, and so on, push on the left in several ways. If you use continuous variable, usually you use the angle of the pole and the angular velocity, for instance. But you can easily see that this is it is not a Markov state, because if you have a high angular velocity and the angle is high, then this is bad, because you want small angular velocity, right? Instead, if the angle is low, then high angular velocity is good, and so on. So there is not a unique answer regarding to that video. The only way to know which was the exact MDP behind that, we should ask to the author of the video. But I must say the cart pole is a toy problem that is usually used to learn reinforcement learning. So it could be a good starting point for start coding and trying techniques and so on. Regarding the continuous state space or action space, I told in the policy learning this lecture, then policy learning methods are good for continuous action spaces, because you can just learn a probability distribution, a parameterized probability distribution.
Yeah, so that's what I was thinking indeed. So that could be an example of potential application, right? Where you have a continuous learning.
Absolutely, yes.
Okay, great, thanks.
Regarding this, I don't know if I told you, policy learning methods in general, when you have a finite actions and you need to learn a policy, that means a probability for every action, you can't have so many actions. I mean, think about 1,000 actions as an upper bound. If your problem has more than 1,000 actions, this is really too much. Probably you don't have methods that are going to work in this case. It's better in that case to model with continuous action space and using the parameterization and a priori knowledge on the shape of the distribution of the action. And in this respect, another research topic, very interesting, is to find methods that work well, that are scalable to more than 1,000 actions. Methods that works well in discrete action spaces with a lot of actions. Open problem.
Can I ask a question? You before said that any task, if properly framed, can be somehow approached with the reinforcement learning. Okay. Can you give me give us a feeling of, I mean, in terms of resource needed, in terms of computation power, in terms of time to train or something like that, when you compare the reinforcement learning to a classical approach, like I can say the other machine learning stuff. I mean, comparing on to reach the same level of performance, if one is easier than the other or not. I mean, if there is some advantage in going reinforcement learning instead of go with another approach.
Well, as I said, I'm not an expert on the other approaches, so I probably can't answer. Let me think. So you would like just an example, right?
Yes, just to understand, when I'm in front of a problem, if I have to give a chance to reinforcement learning or another, and considering also the resource that I have, okay?
Okay, I'm not sure I understand the last part of the question, but let's start with chess. You know, chess in '97 were beaten, humans were beaten by the famous Deep Blue, was called the software. Well, Deep Blue was not reinforcement learning, okay? Simplifying a lot, Deep Blue was made this way. There were very, very skilled human players, chess master, that were saying, okay, in chess, in a chess position, the important features are these ones. And they extracted by hand with a lot of work, with a lot of time, they extracted 8,000 binary features. Okay, so you understand this sentence, 8,000 features extracted by hand. So this was a massive work. And then they started using these features with some approximator to evaluate an approximation of the value function of the chessboard. Okay, so this is just game theory. This is not reinforcement learning. The value function of an NDP is not reinforcement learning. Reinforcement learning is the way you compute the value function. Okay, after a lot of tuning, they decided, so they didn't learn. They decided by human choice the weights to use for each of these 8,000 features. After all of this, they started playing humans and they started fine-tuning either hyperparameters, and at the end they obtained deep blue. Now, I have no idea of the cost, the resources involved in this. And this was 97, so it is more than 20 years ago. But today, or better 2 years ago, reinforcement learning in the declination of the software called Alpha0, which is the Alpha chess, we can call it the version of Alphago for chess, was able to train from zero. That means to extract the features and to train the weights in a completely automatic way without human intervention in less than 3 hours. And in less than 3 hours, he was able to completely defeat, crash completely the best chess software at the time, that was called Stockfish. So this is an example, in my opinion, when the classical machine learning, that is human-tuned features and human estimated weights are much more expensive and costly and less efficient than an automatic reinforcement learning system learning completely from scratch, from zero. But of course, I mean, this is just an example of, I bet there are several examples of problems that you can solve more easily and faster with other machine learning tools than reinforcement learning. The point, in my opinion, is the flexibility of reinforcement learning. If you know reinforcement learning, you can probably try to solve a wide family of problems. I don't want to say every problem, I would say, but I don't want to say every problem, but a wide family of problems. While if you know support vector machines, you can solve a certain family of problems. If you know decision trees or random forest, you can solve another family of problems. If you know, you see several branches of machine learning, you can say, of course, if you are an expert on machine learning, of everything in machine learning, and moreover, you know a lot of reinforcement learning, this is the best you can hope for. Okay, but if I was a student and 20 years old and I had to decide what to study in what to devote my energies and resources, what to study for my future, I would definitely go for reinforcement learning in the very beginning. Reinforcement learning and, of course, neural networks that are paired with reinforcement learning. Does this answer the question?
Yes, give I mean a feeling of that. Maybe just to complete, for Alpha0, which are the resources? I mean, the computing resources we were used. We were talking about very large computation center.
We were still talking about Google, of course, but Alpha0 was also very strict on resources. I remember something like 4 or 5 TPU TPU is this tensor processing unit built on purpose by Google for this kind of problems. So it is not something that you can have. And if you want another estimate, the original AlphaGo that was trained partially in a supervised human way, I mean, not from zero, the very original AlphaGo, it has been computed that in order to replicate on your home computer or my home computer the training made by the original AlphaGo, it would take more or less 4,000 years of computation, night and day.
Okay, they give you an idea.
Give or take. If you want to replicate AlphaGo at your place, forget it. In fact, there are projects, of course, and other research topics parallelizing these techniques, how to use this technique in a more efficient way, in a distributed way. In particular, AlphaGo, there exists a version, and there exist several versions of this. Actually, I'm developing one of them that are distributed. That means that if you want, you can help install my software, and my software will use your computer when there is time and resources to play games, and then it will send these games to me. Now you understand why these games are for. These games are the episodes that are needed by the algorithm to compute targets and to train the approximator. So there are several computers in this moment in the world playing Go games for my software, for other software. The most famous is called Katago at the moment, and the other is Lila Zero. And there are computers in the world playing episodes that are then sent to these algorithms that start training the approximator.
Okay, I think it's time to thank Maurizio again for this very nice course, and thank you all for attending.